that Ashwin mentioned of counting distinct elements, I really want to sort of illustrate a technique in the message passing model, which is very powerful for a number of applications. So this is joint work with Yi Li, Xiaoming Sun, Chenglu Wang, and Qin Zhang. Earlier in the workshop, you've seen this k-party number in hand model. Just to quickly recap, here we have k players, P1 through Pk, who each have their own private input x1 through xk, respectively. And their goal is to compute some function f of their inputs. And we'd like to minimize typically the randomized communication complexity of this task. In this model, we have point-to-point communication, so I'm going to allow every pair of players to be able to talk to each other. And so the model is well defined. We also have that the protocol transcript determines who speaks next. Okay, so the protocol determines who starts, and each message determines who speaks next. So this is the k-party number in hand model. One thing that's often useful is to introduce the notion of a coordinator C. So this could be one of the players, or it could be a new player. And what we do is we route all communication through this coordinator. Okay, so this only changes the communication by a factor of 2. So if Pi wants to send a message to Pj, now the player tells the coordinator to send the message to Pj. So the message gets sent twice. And also, there's an additional word per message where the player, since the player has to specify who the recipient of the message is. But for this talk, we're going to ignore these factors. Okay, so yeah, there are a number of problems looked at in these models. So database problems. You have a database which is partitioned across multiple servers, and they might want to estimate statistics of this database, such as distinct elements or frequency moments. Linear algebraic problems. Maybe everyone has a matrix, and you want to know if the sum of the matrices is invertible. Or maybe you want to solve a linear system, which involves the sum of these matrices. Graph problems. Maybe everyone has a disjoint subset of edges of a graph, and you'd like to know if the graph is, say, connected or bipartite. Okay, so these are some problems. So for this talk, what I'm going to do is focus on a distributional communication problem, which I'll call sum disjointness. And yes, I won't get into the details of how to apply this to these applications, or sort of variants of this problem, which are more useful for some of the applications. Okay, so let me just say some notation here. So for sets S and T, define the disjointness function, the standard notion of disjointness. So disj of St is 1 if the sets S and T intersect, and it's 0 otherwise. Okay? So I'll use this throughout the talk. So what is the sum disjointness problem that I'm talking about? So it's the following, okay? I'll describe it here, but what you're going to think about is having the coordinator trying to solve a disjointness instance between each of the players. Now let me describe this more formally. So it's a distributional problem. So let S be a random subset of 1 through n. And you can think of this as being the input to the coordinator. Okay? And now we're going to define how we give the inputs to the remaining players. So independently for each of the players, with probability 1/2, we give the player Pi a random set Ti, subject to the condition that it intersects S. And with remaining probability 1/2, we give it a random set Ti so that it doesn't intersect the set S. So I didn't really specify how you choose Ti condition on it intersecting S or not condition on intersecting S, but let's ignore that for now. I'll mention that a little bit later. So this is these are the inputs to the problem, and what is the problem? So the problem is it's a promise problem, and what they'd like to do is they want to know if the number of sets that intersect S is at least k over 2 plus root k, or at most k over 2 minus root k. Okay, now note by standard anti-concentration of the binomial distribution, one of these cases is going to happen with large constant probability. And given that you're in one of these cases, you'd like to know which one. And so the result that I'll describe here is that you can show that the randomized communication complexity of this task is omega n times k. Okay, so n is the sort of the universe size of a disjointness instance, and k the number of players. And note that all these disjointness instances, are heavily correlated, right? They're all using the same set S of the coordinator. Okay. So, let me try to show this an outline of the proof. So to study this problem, let's introduce a simpler problem called the gap threshold problem. Okay, so in this problem, again in this k-party number in hand model, player pi now only holds a bit zi, okay, instead of a set. And the zi are independent fair coin tosses across the k players. And what they'd like to do is decide the following. Is the sum of the coin tosses, the sum of these Bernoulli 1/2 variables, at least k over 2 plus root k, or at most k over 2 minus root k. Okay, and as before, otherwise we don't care. It's a distributional problem. Okay, so can we show a lower bound for this problem? So intuitively, omega k bits of communication seems like a lower bound for this problem. A natural protocol would be to try to sample players and look at the sum of the samples and use that to try to estimate the overall sum. So this doesn't work. This needs k samples. But how do you formally prove this lower bound? Okay. So we're going to use the rectangle property of communication to show this this claim, which is very important for the proof. It's the following. So the players run this protocol, a k-party protocol for this simpler gap threshold problem. And at the end of the protocol execution, there's some transcript tau, which includes all the messages and the output. And the claim is that these bits, z1 through zk, are independent, even conditioned on the value of the transcript. Okay? So they started off as independent, Bernoulli 1/2 variables. And after you run this protocol, I claim they're still independent, though they're no longer fair coin tosses. So why is this? So let's just assume for now that the players are deterministic. We're proving a lower bound by Yale's principle. I'll mention how to extend this to randomized, which is sometimes useful in the context of larger problems. But let's just assume they're deterministic for now. So what is the input vector to this problem? So everyone has a bit. So the input is just this vector z, this bit string of length k. Okay, and everyone has a IID coin toss, so the distribution on the inputs is uniform. And the claim, this is a property of communication, that you take this input space, 0, 1 to the k, and you cut it up into combinatorial rectangles. Each transcript tau corresponds to one of these rectangles. And these rectangles have this nice product structure. So one of these rectangles, S, it looks like S1 cross S2 cross Sk, where in this case, each Si is in 0, 1, is a subset of 0, 1, since the input is a bit. Okay, in particular, Si can be the full set 0, 1, or 0 or 1. Okay, this is a simple setting. So now, since these coin tosses Zi were independent to start with, now let's condition on the value of a transcript. So we condition on this set S. So what we have is conditioned on this. We have a random preimage of this set S. And because of this product structure, what this means is actually that, exactly the statement that I'm trying to show, that the Zi's are independent condition on this transcript. right? So because of this product structure, what happens is that each zi condition on the transcript is either still a random bit, or it's fixed to 0 or fixed to 1. Yeah, okay. Okay, so this is an important property. So now let's try to, so where are we? We're trying to prove this omega k lower bound for this gap threshold problem. Everyone has this fair coin toss. And yeah, the coordinator is trying to decide if the sum is greater than k over 2 plus root k, or at most k over 2 minus root k. And now, as I just said, that by independence of these bits conditioned on the transcript, this is equivalent to fixing some of the zi's to be 0 or 1, or to be Bernoulli 1/2 after the protocol execution. Okay, so how can we use this, this property? So I'll just present a short sequence of lemmas which capture the ideas for this. So the first lemma I want to call the unbiased conditional expectation lemma. And what this says is the following. So there's some notion of a transcript distribution, right? There's an input distribution, then I run this deterministic protocol, and I get a distribution on transcripts. And what I'm saying is with probability 2/3 over the choice of a transcript from this distribution, the expectation of the sum of these condition bits is not too far from what it was before. It started off as k over 2, and now I'm claiming the expectation is within, say, 100 root k of k over 2. Now, why is this? I mean, this is certainly not true for all transcripts. I'm just saying with good probability this happens. Why is this true? Well, one way to see it is the following way. So consider any transcript tau. These are just bits. These zi's conditioned on tau, so the variance is at most k, okay, of this sum. Now, basically, if I condition on tau and I look at these bits, since the variance is at most k, I'm going to deviate from my whatever my expectation is by about root k. So one way of sampling an input is to first sample a transcript and then sample an input condition on the transcript. Now we know if we just sample an input, then the sum of the zi's is going to be very close to k over 2 with constant probability. But if this statement did not hold, then basically I could sample a transcript, and now I'm 100 root k away from k over 2. And then I could sample an input condition on that transcript, and by Chebyshev's inequality I'm close to that expectation, which means that, you know, with good probability I'm 50 root k away from k over 2 for one of the inputs, which can't happen, right? Because we know the inputs are binomially distributed, so they're close to k over 2. Okay, so this is saying that, you know, for a typical transcript, the expectation remains close to what it was before the conditioning. This is the first lemma. And note that that lemma didn't even use that communication was small or anything like that. The second lemma does use the fact that I'm going to assume the communication is little o of k and get a contradiction. And this I call lots of randomness after conditioning. So here is, if the communication, total communication is little o of k, then for most of these indices, you know, so then for a typical transcript, for most of the indices I, we have that the conditioned random variable zi condition on tau is still a fair coin toss. Right? Now this just follows by counting, right? We're partitioning this input space 0, 1 to the k into pieces. If we fixed all the bits, we would have way too many pieces, and the communication is log of the number of pieces, we would get a k lower bound. So, okay, so yeah, so we have these two properties. The expectation is close to k over 2, and most of these are still IID Bernoulli 1/2. Okay. So let's you know, condition on a tau satisfying these two lemmas, which happens with good constant probability. And so now the whole proof is just based on an anti-concentration observation. So we fix such a tau. And now let's look at the following, right? So most of these bits conditioned on tau are still, you know, fair coin tosses. So they have a lot of deviation. I mean, so in particular, you know, with probability, a small constant probability, 0.001, these things will be more than 100 root k away from whatever their expectation is in either direction. Well, that's a problem, right? Because the expectation is within 100 root k of k over 2. And these things are deviating by more than 100 root k in either direction. So in particular, they're k over 2 plus root k or k over 2 minus root k with some small constant probability. But the output is just based on this transcript. And so the protocol has to fail with this probability, this 0.001. Right? So basically, with good probability, I sample a transcript, and condition on that, then I have this good probability of this reasonable probability of failing. So the protocol, if it uses much less than k communication, fails with some constant probability. Okay, so right. Okay, so let me just so this is actually the whole proof for the deterministic distributional case. Let me just mention a simple extension. So when the players have their own private randomness, the proof generalizes. You just think of the randomness as being part of the input, and now it's the randomness together with the input bit, and the generalization of this. So now the zi's conditional on transcript are no longer just Bernoulli 1/2. But what you can show is an analogous statement that for most of the, for a typical transcript tau, for most of the indices, the entropy is considerably reduced, right? It started off as 1, and it goes down to something very small. So a correct protocol must satisfy this property. Okay, so now let's go back to this original problem that we were interested in, which is the sum disjointness problem. Okay. So we call these input sets Ti intersect some set S. We chose this random set S to give to the coordinator, and now let's do the then we chose this Ti's independently to intersect S with probability 1/2. So let's think of the following. Let's think of embedding this gap threshold problem inside of this sum disjointness problem. Okay. So suppose I just have these uniform random bits Z1 through Zk. That are inputs to the gap threshold problem. What I'm going to do is for each player pi, if zi is equal to 1, then I'm going to choose a random set Ti so that the disjointness, so that Ti intersects S. Okay? And if zi is equal to 0, then I choose Ti so it does not intersect S. So what I'm doing is I'm encoding the inputs to this gap threshold problem as the outputs of these k disjointness instances. Okay. And recall earlier, what is this problem? We're trying to figure out if the number of sets which intersects S is at least k over 2 plus root k, or at most k over 2 minus root k. Or equivalently in this notation, we're trying to figure out if the sum of these zi's, these output bits, is at least k over 2 plus root k, or at most k over 2 minus root k. Yeah.
Specify how you select them to intersect.
Yeah, so I won't get in. Let me just say how you do it. So you do it in Razborov's distribution, basically. So what you do is you choose them to intersect at a unique random position of S, and they actually have size n over 4 instead of n over 2. But I'll use that result as a black box, basically. So in this notation, this is what they're trying to solve. Okay, so I can use this. So this is a protocol which is solving this problem. And by the previous analysis, a correct protocol for this satisfies the property that the probability of our transcripts for typical, for most choices of indices, the entropy of Zi is reduced conditioned on the transcript. This was what we proved about gap threshold. Okay? And we saw that the output of this problem is solving this gap threshold problem. Okay, so this is sort of the embedding argument. Okay, but these Zi's are the output bits of these disjointness instances. Right, so what's happening here is most of these disjointness instances are actually being solved by the protocol. I can run the protocol and I can look at the transcript and I can figure out these bits, Zi, the output bits. Okay, so this is now where we, at this point, we're going to try to get a contradiction by reducing to a two-player problem. Okay, so we have this property. And now suppose the overall communication were much less than k times n. Okay, so then by averaging, there's a player pi, so that typically the communication between the coordinator and pi is much less than n. Okay? And moreover, just by a union bound, since for typical transcript, most of these output bits zi have their entropy reduced, so this player pi has that this hzi condition on tau is small with large probability. So what we've done is we found a player for which the transcript typically reveals the output bit of the disjointness instance between the coordinator and that player, and moreover the communication with that player is small. So that should suggest, these are two players in this k-player network. This should suggest a way of proving a lower bound, and it does. So the idea is to now reduce to this two-player problem. So consider, so you have two players in a disjointness problem, and let those two players be identified with the coordinator and this player pi that we fixed on the previous slide. Okay, so what they do is, so let me just say, if the coordinator has some input set to this two-player disjointness problem, that becomes the set S that we said we could think about as the coordinator having. And the player pi's input is this ti. Okay? But the nice thing here is that this coordinator, there are only two players now, but the coordinator can pretend like there are k players. And what it can do is, using its input set, it can sample the inputs to all the remaining players. Right? How do we give the inputs to these remaining players? We said independently with probability 1/2, I choose it to intersect the coordinator set, and with probability 1/2, it doesn't intersect the coordinator set. So the coordinator can generate all the inputs for all the remaining players. And now they can run the k-player protocol. But the point is here, messages between the coordinator and players pj for j not equal to I, they can all be simulated by local computation. There's no actual communication. Right, so the only communication is between the coordinator and the ith player, and if this communication is little of n, this contradicts distributional lower bounds for the disjointness problem. Okay, does that make sense? Okay, so that's an example of how reducing to two players, and an example of using composition. So let me just conclude. So this is a composition technique for proving lower bounds here, which is quite useful for problems like estimating distinct elements in this model. There are other nice techniques by Braverman et al. And Rodham and others, which look at k-party disjointness in this message passing model, which is a different notion than the disjointness instance that we looked at here. There's also a symmetrization technique of Phillips et al., which this sort of implicitly builds upon. Which it builds upon. There are many tight lower bounds for problems in this model. So statistical problems, graph problems, and linear algebra problems, a lot of these have been resolved. And let me just mention some future directions. So I don't think rounds versus communication is very well understood in this model at this point. So that's one thing. Another very nice work of Arkady, J. Kumar, and Atriruda is for topology-sensitive problems. So instead of allowing all players to be able to talk to each other in a point-to-point fashion, there's some topology, and you get communication bounds that depend on that topology. So that's all. Thanks.
Questions? Could you say a few words about how it applies to the problem of counting distinct elements?
So for that problem, everyone has a database, and they want to know. I put all these databases together, and I want to know if is the number of distinct elements. I want to get a 1 plus epsilon relative approximation to the number of distinct elements, number of distinct records in this database. And for that problem, you can prove a k over epsilon squared lower bound, where k is the number of players and epsilon is this approximation factor. And the 1 over epsilon squared factor maps to this n in this disjointness setting. And there's also a variant of this threshold sum problem you need, which is not checking if the majority is, is biased away or biased towards, you need a threshold at a very different level, not even a constant factor times k, but a very low level. And you can also generalize this to get lower bounds for that. And sort of what happens here is this this k over 2 plus root k. This translates into the root k is giving you the approximation factor. This gap translates to a 1 plus epsilon approximation if you set all these parameters appropriately. But it's a very high level intuition. But
Thanks.
okay.